Alright, gang, here we go. Chem 2 Unit 11. We're talking about standard entropies. Alright, so now we're going to start getting into a little bit of math. It's not too bad. In fact, some of you guys will really like it because it harkens back to previous, more simple times. Okay, so standard entropies. One tricky bit here is remember when we talked about standard entropies of formation, life wasn't so, or life was nice and simple. If we had our elements, those elements had a standard entropy or enthalpy of formation of zero because they were in their natural state. But because remember, the only time you'd have an entropy of zero is when you are at absolute zero. So that is our reference. Entropies for elements are not zero, not zero. So you got to have a big old table to look at them all. Look at them, and we'll look at that here in a second. Some things to be careful of is that your standard molar enthalpies for gases are generally greater than liquids. Be careful of size. Also be careful of units. Units, that's one of the trickiest bits here when we start getting into Gibbs free energy in the next part is the idea that entropy is almost always in joules per mole Kelvin, but but enthalpy is in kilojoules per mole most times. All right. You'll also notice that your standard entropies increase with increasing molar mass, right? And then standard entropies also increase with the more atoms in a formula. We kind of talked about that in a previous video. So here we go. So here's a bunch of standard molar entropies. Notice hydrogen is pretty low, 130. Water is even lower than that when it's a liquid, but as a gas, right, it's at 188.8, which makes sense, right? This kind of matches up what we talked about in previous video. There's water as a liquid versus water as a gas. All right, and then there's benzene and a bunch of solids. Notice how small the solids are. Like the smallest one on here is that iron solid, nice and handy. All right, and then in order to use these to calculate enthalpy changes, all you have to do is you sum up the products times their coefficients in their balanced chemical equation and then subtract out the reactants. So it's the same thing we were doing back in a previous unit. It's just products minus reactants. That's all it is, products minus reactants. So a couple practice problems is we're going to predict some relative entropies. All right, kind of using some of those points we had in that previous slide, and then we're going to do one math problem, just one. All right, it says in each pair, choose the system that has greater entropy and explain your choice. So it says 1 mole of sodium chloride solid or 1 mole of hydrochloric acid gas. Well, shoot, man. I mean, the gas is going to have higher entropy. It doesn't really matter what is in the solid. You know, they got equal moles. They're both the same temperature, so the gas, it's the gas. No problem. All right, this guy, part B, says 2 moles of HCl or 1 mole of HCl, both at the same temperature. Well, 2 moles will have twice as many microstates because there's twice as many particles, so it should have twice the entropy, right? Easy peasy. All right, and then part C, 1 mole of HCl gas or 1 mole of argon gas at 298 Kelvin. So let's see, let's pull out the periodic table here. So argon is 39.48. HCl would be like 36. So they're essentially the same mass. So I would say that HCl is going to have more microstates available because you're going to have a vibrational and a rotational microstate to worry about. So I would say this here. I would say HCl has more microstates available, so therefore it has a higher entropy. All right. All right, here's our practice problem right here. Sorry. All right, it says calculate the change in standard entropy of the system for the synthesis of ammonia from N2 and H2. So this is the Haber process is what this is. All right, so here we go. So change of entropy, right? We use these standard entropies. They got it here for us. So remember products minus reactants. So we'll take products. There's only one product, so we say 2 times the standard entropy of ammonia. So we find ammonia, NH3. Where'd you go? There you are, 192.5. So we say 2 times 192.5. All right, and then we're going to subtract out the reactants, products minus reactants. So we have 1 N2. So N2 is right here at the top, 191.5, and plus 3 times hydrogen, which is 130.6. So our delta S is equal to, let's see, 2 times 192.5 minus 1 times 191.5 plus 3 times 130.6. I got negative 198.3, and our units would be joules per mole Kelvin. And that's that. That's really all it amounts to right there. You need to be able to calculate entropy like that because here in the next bit, it's going to get a lot more exciting. Now we'll finally start to be able to use, well, what the heck is entropy? How is this helpful for me actually doing chemistry? And so if you're really worried about that, stay tuned to the next video. See you on the flip side.